Hello everyone and welcome to this week's lecture. Today we'll go back and revisit deep learning, but this time we'll do so in a much more detailed manner to get started on our deep learning. So deep learning is a wide family of techniques for machine learning in which hypotheses takes the form of complex algebraic circuits with connections that we can tune. Okay, so if you remember when we did logistic regression and after that we did non-parametric models, we said the goal is to, given a set of hypotheses, to find the best hypothesis to fit the training data without overfitting so that it can generalize well. So in deep learning case, the hypotheses we're selecting from are complex algebraic circuits, essentially, that you will see are made of neurons, and these neurons have weights or activation that vary in strengths, and they determine which hypothesis we come up with at the end. So the word deep refers to the fact that the circuits are typically organized in many layers. So for deep learning to be able to really distinguish itself from other machine learning approaches like logistic regression or support vector machine, the idea here is that instead of using one very large layer, we're going to instead use a bunch of connected layers one after the other that will allow us to capture more nonlinearity in the data than we could with just a flat model like logistic regression. So this means that the computation path from input to outputs will have many steps. So deep learning is currently the most popular approach for applications like visual object recognition, machine translation, speech recognition, speech synthesis, and image synthesis. It also plays a significant role in reinforcement learning applications that we will discuss later in this class. So deep learning has its origin in the early work that tried to model networks of neurons in the brain with computational circuits. For this reason, the networks trained by deep learning methods are often called neural networks. As you can see, there's a very lot of similarity between how each neuron in a deep learning model works or is activated or modifies the data as to what happens in a neuron in the brain. Even though the resemblance to real neuron cells and structure is just very light, but it's still there is some resemblance. So so it's not really clear essentially why deep learning became the most successful machine learning approach as it is today, but it has a lot of advantages, as you will see, compared to the methods we discussed previously, like regression and non-parametric methods, KNN and all these methods, especially for higher dimensional data like images. So, for example, although methods like linear and logistic regression can handle a large number of input variables, the computation path from each input to the output is very short. So essentially you multiply by a single weight. Then you add the aggregate output. Moreover, the different input variables contribute independently to the output. There's no interaction between the different input. Each input gets its own weight, and then they're finally combined in the output. So this limits the power of such models. They can't really capture interactions between the different inputs, and they can't really model nonlinearity as much. So they can only represent linear functions and boundaries in the input space, where in reality most real-world problems are far more complex than just linear models. We also looked at decision trees. So decision trees allow for long computation paths. That's true. That can depend on many input variables because you have multiple layers there. But only for a relatively small fraction of the possible input vector. So if the decision tree has long computation paths for a significant fraction of the possible inputs, it must be a very large tree in the number of input variables. So the basic idea of deep learning then is to train circuits such that the computation paths are long, okay, allowing all the input variables to interact in complex ways together, which allows us to capture any nonlinearity. These circuit models then turn out to be very expressive and capable of capturing complexities in real-world data, like in images and language, for many important kinds of learning problems. So we're going to start this chapter by describing simple feedforward networks, their components, and the essential learning in such networks. Then we'll get into more detail on how deep networks then are constructed based on that simple feedforward networks. Then we're going to cover what's called convolutional neural network, which are very important for vision applications, which of course are essential for computer vision problems like self-driving cars and image, adding caption to images and so on. We'll also discuss some methods for avoiding overfitting because it's very easy to overfit once the network becomes so powerful. It's very easy to just overfit the entire training data. And then we look also at the recurrent neural networks, which are perfect for sequential data like time series analysis and natural language processing, obviously. Okay, so let's start with simple feedforward network. So a feedforward network has connection only in one direction, which is essentially forward, right? Like the name suggests. So it forms a directed graph with designated input and output nodes. Each node then computes a function of its input and then passes its output, which is the result of its computation, to the successors in the network, whether that successor is in another network, another layer, or an output layer. So information flows through the network from the input nodes to the output nodes, and there are no loops. Okay, so this is a feedforward network. On the other hand, we have a recurrent network, which feeds its intermediate or final outputs back into its own input. So there are loops in this case because we take its output and we feed it back as an input to the same network. This means that the signal values within the network form a dynamic system that has internal memory, okay, because it remembers what was the output that was generated. And this will be very useful when we're doing time series analysis and treating with any data that comes in sequential manner, like sentences or text, for example. Now, Boolean circuits, which implement Boolean functions, are an example of feedforward network. So in one of your assignments, either you did it already or you'll be doing it soon, you'll have to implement a network to design a network to implement the XOR function. So in that case, for the Boolean circuit, the inputs are limited to 0 and 1. And each node implements a simple Boolean function of its input, and or essentially producing another 0 or 1. In neural networks, on the other hand, input values are typically continuous. They're not binary numbers. And nodes take continuous inputs and produce continuous outputs. So we will apply different application functions to that input and get an output from it. Some of the inputs to the nodes are parameters of the network. And in this case, what we mean by parameter is that something that we can tune as we train the network in order to get an output, the output that we're expecting from the network. As you remember, the entire goal of this is to minimize the loss function. So you can see that these parameters will be tuned to minimize the loss function of the entire network. So the network learns by adjusting the values of these parameters so that the network as a whole fits the training data. And how do we measure if a network fits the training data? By the loss function. So we start by defining our loss function. Again, we have two cases. If we're trying to predict a continuous variable, we're going to use an L2 loss function, see how far our prediction is. If we're trying to solve a classification problem, then we're going to use a loss function similar to the one we used in logistic regression. So networks as a complex functions. Let's look more at how can we express a neural network as a complex function. So each node within a network then is called a unit. And traditionally, a unit calculates the weighted sum of its input from its predecessor node, or if it's an input layer, then from the input, and then applies some nonlinear function to produce its output. Okay, so that's essentially what each neuron does in a neural network. So it's going to calculate the weighted sum of the input and then apply some nonlinear transformation. So for example, if we let Aj be the output of unit J, and Wij be the weight attached to the link from the unit I to the unit J, so input I and unit J that we're talking about, then we have Aj, which is the output from that unit, is going to be some nonlinear function Gj, okay, we call it the nonlinear activation function of unit J, and it's going to be applied to the weighted sum of all the input from the previous layer AI. Okay, so essentially all the inputs to the unit Aj are coming from the previous input, from the previous layer I. So we get the weighted sum of those inputs in the summation there, and then we apply our nonlinear activation function to get the output. So the term activation function is very important here, and as you will learn, the choice of activation function, softmax activation, ReLU, or there are many hypertangential activation and so on, depends on the problem we're working on. Some activation functions work better than others in specific cases. So that's another choice you have to make in order to limit the set of hypotheses that we're going to explore. Okay, I'll see you in the next part.